Welcome to tonight's journey into the hidden depths of our planet. The world above rests beneath a quiet blanket of stars. You can let go of the day and embrace the stillness. Your breathing matches the slow rhythm of the ocean tides. A peaceful night has fallen across the northern hemisphere. City lights fade into the vast expanse of the open sea. We turn our attention away from the busy terrestrial world. A massive underwater realm awaits our quiet and patient observation. Tonight brings us to the frigid waters of the far north. We explore a submerged marvel known as the Iceland Vents. This is a unique place where fire meets the icy ocean. Relax your mind as we prepare to explore the deep. The ocean offers a perfect sanctuary for uninterrupted rest. Let the gentle current carry your thoughts away into the dark. Our expedition takes place in the remote northern Atlantic Ocean. We are positioned just below the invisible Arctic Circle. The exact coordinates read 66 degrees north latitude. The longitude marks exactly 18 degrees west of the prime meridian. This puts us just offshore from the northern coast of Iceland. The surface waters here remain incredibly cold throughout the entire year. Winter ice floes often drift across these exact nautical coordinates. Surface temperatures hover merely a few degrees above the freezing point. Frigid winds sweep across the unbroken surface of the water. The Kolbeinsey Ridge stretches across this isolated oceanic sector. It forms a critical segment of the global mid-ocean ridge system. This ridge connects the massive Atlantic basin to the Arctic Ocean. Navigating these waters requires highly specialized maritime research vessels. The sea state is often rough and unforgiving to surface ships. Beneath the turbulent waves lies a completely silent and still world. The Earth's crust is deeply fractured along this extensive boundary. The North American tectonic plate pulls away from the Eurasian plate. This immense geological divergence occurs at a steady, measurable pace. The massive plates separate by about 10 millimeters every single year. Magma rises slowly from the mantle to fill this expanding gap. The seafloor constantly renews itself through this endless volcanic process. This tectonic scene creates a dramatic and rugged underwater mountain range. Deep rift valleys run parallel to the towering basalt ridges. The crust here is unusually thin and highly geologically active. Geothermal energy radiates outward from the deep, hidden magma chambers. Fault lines create complex networks of cracks across the ocean floor. Seawater seeps downward into these porous volcanic rock formations. The water travels kilometers deep into the heated oceanic crust. Intense subterranean heat alters the chemical composition of the seawater. The fluid absorbs heavy metals and sulfur from the surrounding rocks. This superheated mixture eventually forces its way back to the surface. The resulting hydrothermal vents form spectacular chimneys on the seafloor. These structures are the primary focus of our nighttime exploration. The tectonic forces at work here are both ancient and ongoing. They shape the very foundation of the global ocean basin. Scientists first documented this specific vent field in recent decades. Marine geologist Dr. Sven Petersen led early mapping expeditions here. Sonar scans revealed towering mineral chimneys rising from the seabed. These acoustic maps provided the first glimpse of the vent field. Researchers deployed autonomous underwater vehicles to gather high-resolution imagery. The robotic subs captured detailed photographs of the geological formations. They recorded significant temperature anomalies in the near-bottom water layers. Chemical sensors detected high concentrations of dissolved hydrogen sulfide. This chemical signature is a classic indicator of hydrothermal activity. The discovery expanded our understanding of Arctic deep-sea ecosystems. Geologists named several individual vent structures based on their unique shapes. Some chimneys resemble ancient ruined castles made of dark stone. Others look like slender spires reaching upward into the dark water. The mineral deposits contain valuable elements like copper and zinc. These elements precipitate out of the fluid when it hits cold water. The accumulation of minerals builds the chimney's layer by microscopic layer. This slow construction process takes thousands of years to complete. The scientific community continues to monitor this site for seismic activity. Earthquakes frequently shake the ridge as the tectonic plates shift. These tremors can alter the flow of the deep hydrothermal fluids. We focus our instruments on a depth of 400 meters. Some vent structures plunge even deeper to 1,000 meters. At 400 meters down, sunlight completely loses its power. The photic zone ends far above our current oceanic position. Photosynthesis cannot occur in this permanent and absolute midnight environment. The water column presses down with immense physical weight. No surface storms or weather patterns disturb this deep realm. The temperature of the ambient seawater is roughly 2 degrees Celsius. This near-freezing environment remains remarkably stable throughout the entire year. Seasonal changes on the surface have absolutely no effect down here. The eternal darkness is absolute and completely devoid of natural light. Only bioluminescent flashes occasionally break the deep oceanic gloom. These tiny sparks of light come from passing deep-sea organisms. The vast majority of the time, the darkness remains total. Our submersible relies entirely on powerful exterior LED floodlights. These artificial beams cut through the murky, mineral-rich ocean water. The light reveals a landscape that has never known the sun. Shadows stretch long and dark behind the towering rocky formations. The complete absence of light creates a profound sense of isolation. It is a peaceful solitude that encourages a quiet, resting mind. The hydrostatic pressure at this depth is truly formidable. It measures approximately 40 atmospheres of absolute physical pressure. This equals 400 tons of force per square meter. Human lungs would instantly collapse under such extreme environmental conditions. Our specialized submersible is built from thick titanium alloy spheres. The reinforced hull easily withstands the crushing oceanic weight. Every 10 meters of water adds another full atmosphere of pressure. The surrounding fluid is dense and heavy with dissolved minerals. Water behaves quite differently under these extreme atmospheric loads. The boiling point of seawater alters dramatically in this deep environment. At standard surface pressure, water boils at 100 degrees Celsius. Down here, the immense pressure keeps superheated water in a liquid state. The vent fluids can reach temperatures of 300 degrees Celsius. Yet, this incredibly hot liquid never actually turns into steam. It remains a dense, shimmering fluid as it exits the crust. The contrast between the hot fluid and cold seawater is stark. Our sensors carefully monitor the pressure differentials outside the hull. The engineering behind our vessel ensures a perfectly safe journey. You are completely secure within this highly protective titanium shell. The heavy pressure outside only deepens the feeling of inner safety. The seafloor terrain consists primarily of jagged volcanic glass. Pillow lavas form rounded, bulbous shapes across the ocean floor. These formations occur when molten rock meets freezing seawater. The rapid cooling creates a shattered, highly brittle basaltic crust. Fissures crisscross the rock, venting small streams of warm fluid. The eternal darkness hides these geological scars from human eyes. Only our artificial lights reveal the harsh and uneven landscape. Fine marine snow drifts continuously toward the barren ocean floor. This organic debris settles softly into the deep volcanic crevices. The landscape heavily resembles a barren, desolate alien world. Steep cliffs of black rock rise suddenly from the flat plains. Deep trenches drop away into unmapped and unexplored abysses. The topography is chaotic, shaped by violent, ancient tectonic forces. Layers of sediment are remarkably thin in this active region. The new oceanic crust has not had time to accumulate debris. Fresh lava flows appear dark and glassy under our bright searchlights. Older rocks are coated in a fine layer of rust-colored minerals. Iron oxide precipitates out of the water, painting the rocks red. The visual contrast between black basalt and red iron is striking. This is a unique landscape of stark extremes and quiet beauty. Our instruments detect a sudden change in the local water chemistry. The dissolved oxygen levels drop significantly as we move forward. Methane concentrations rise, indicating our close proximity to the active vents. The water becomes cloudy with thick suspended particulate matter. These particles are tiny specks of precipitated sulfide minerals. They catch the light from our submersible like a swirling snowstorm. This underwater blizzard is a classic hallmark of hydrothermal activity. The surrounding currents carry these minerals far across the ocean basin. They provide essential nutrients to distant, nutrient-poor marine environments. Swirling thermal gradients distort the visual field outside our thick window. The water shimmers and dances due to the intense heat exchange. This specific optical illusion is known scientifically as the Schlieren effect. It makes the rocky seafloor appear to ripple and move constantly. The dynamic environment is entirely driven by the Earth's internal engine. We navigate carefully through this complex and shifting thermal landscape. The precision of our thrusters keeps the vessel perfectly stable. The submersible hovers silently above a massive basaltic plateau. We have reached our primary observation point for the long night. The coordinates match Dr. Peterson's original geological survey maps exactly. We are perfectly positioned to observe the Iceland Vents in detail. The mechanical hum of our engines fades into the quiet background. A profound silence settles over the comfortable interior of the cabin. The darkness outside the viewport is vast and completely all-encompassing. It wraps around our small vessel like a heavy, protective blanket. The extreme isolation of the deep sea brings a unique peace. There are no digital distractions or modern worries down here. The geological puzzle of the northern oceans began decades ago. Scientists long suspected thermal activity beyond the Icelandic coast. The mid-Atlantic ridge continues directly beneath the Arctic waters. Early oceanographers studied the Kolbeinsey Ridge in the 1970s. They mapped the seafloor using primitive acoustic sounding techniques. The data showed unusual topographic rises along the fault line. Researchers noted significant magnetic anomalies across the ocean floor. The tectonic plates here pull apart at a steady rate. Magma rises close to the crustal surface almost constantly. This creates an ideal environment for deep hydrothermal circulation. Yet direct evidence of underwater geysers remained entirely elusive. The harsh Arctic weather hindered extensive maritime exploration efforts. Winter storms made research ship navigation incredibly dangerous. Ice coverage restricted access during many months of the year. Marine geologists had to wait for better deep-sea technology. By the early 1990s, chemical oceanography advanced quite significantly. Researchers began testing the water column for specific trace elements. They deployed heavy rosette samplers from large research vessels. These instruments captured water at highly specific depth intervals. Laboratory analysis revealed elevated levels of dissolved methane gas. Scientists also found distinct helium-3 isotope signatures in the water. This specific isotope indicates a direct and active mantle source. The chemical plumes drifted miles away from their original origins. Deep ocean currents carried these volcanic gases steadily southward. A team from the University of Iceland tracked these signals. They focused on a region just north of the island. The coordinates centered exactly around 66 degrees north latitude. The initial search grid covered hundreds of square kilometers. They needed precise bathymetry to narrow the primary target area. High-resolution multibeam sonar provided the necessary seafloor maps in 1995. The first breakthrough occurred during a summer expedition in 1997. The German research vessel Poseidon sailed into the Arctic Circle. Chief scientists Carl Gronwald and Peter Hersig led the mission. They targeted the Tjorns fracture zone north of Iceland. The ship hovered precisely over a depth of 400 meters. Technicians lowered a towed camera sled into the freezing water. The instrument package included a highly sensitive temperature probe. Real-time data showed a sudden thermal spike near the bottom. The ambient water temperature normally hovered around 2 degrees Celsius. Suddenly, the digital sensors registered a jump to 10 degrees. The camera feed transmitted grainy black and white video images. Researchers saw massive fields of white bacterial mats below them. These microbial structures covered the dark basaltic rocks quite extensively. Soon, the camera revealed actively venting hydrothermal chimney structures. Around the same time, another discovery happened closer to shore. Icelandic diver Erlendur Bogason explored the Dark Age after a fjord. He investigated local fishermen rumors of warm ascending water currents. In 1997, he found the massive Striton hydrothermal chimney. This structure stood remarkably close to the actual ocean surface. The mineral peak reached within 15 meters of the waves. It remains the shallowest known hydrothermal vent globally today. Bogason observed fresh hot water pouring from the mineral cone. The vent fluid measured a blistering 72 degrees Celsius. Magnesium silicate formed the towering chimney walls over many millennia. The surrounding seawater contained high concentrations of dissolved minerals. When the hot fluid met cold seawater, rapid precipitation occurred. This chemical reaction continually added solid material to the structure. The Striton discovery proved vents could exist in coastal waters. These initial finds prompted much larger international scientific exploration efforts. The Advanced Deep-Sea Research vessel Meteor arrived in 2004. Scientists wanted to explore the deeper Kolbeinsey Ridge fault segments. They deployed the capable remotely operated vehicle known as Quest. This submarine featured high-definition video cameras for clear observation. It also carried precise robotic manipulator arms for geological sampling. The ROV descended smoothly to a depth of 1,000 meters. The pilot navigated carefully through steep and jagged volcanic canyons. Sonar indicated a large geological structure ahead in the gloom. The vehicle lights illuminated a massive and active hydrothermal field. Researchers officially named this new area the Seven Sisters Site. The location contained multiple active chimney structures clustered tightly together. Some of these mineral chimneys reached heights of 10 meters. Hot vent fluids gushed from the rocky orifices quite constantly. The Quest ROV inserted a titanium temperature probe into a vent. The digital readout climbed rapidly within just a few seconds. The fluid temperature peaked at exactly 250 degrees Celsius. This extreme temperature falls below the boiling point at this depth. The immense hydrostatic pressure keeps the superheated water in liquid form. Scientists collected pure fluid samples using specialized titanium syringes. They needed to prevent any contamination from the surrounding seawater. The subsequent chemical analysis revealed a highly unique fluid composition. These northern vents contain very low concentrations of heavy metals. Typical black smokers emit dense clouds of iron and sulfide. The Iceland vents produce mostly clear or milky fluid emissions. Extremely high concentrations of hydrogen gas characterized these specific emissions. This unique chemistry results from the specific underlying basaltic rocks. The magma composition here differs greatly from the southern Atlantic. Biologists eagerly awaited the first physical samples from the seafloor. They fully expected to find familiar hydrothermal vent animal species. Mid-Atlantic vents normally host massive swarms of blind Rimicaris shrimp. The ROV cameras revealed a completely different and strange ecosystem. The expected shrimp were entirely absent from these northern fields. Instead, researchers found dense colonies of small marine gastropod snails. Thousands of tiny limpets covered the active mineral chimney walls. Unidentified species of amphipods swam through the warm fluid currents. Biologists collected several delicate specimens using a robotic suction device. The samples went straight into refrigerated containers on the ship. Later genetic testing proved many of these species were entirely new. This complete biological isolation puzzled the international scientific community greatly. Deep water currents apparently prevented any larval migration from the south. Exploration moved even further north in the subsequent following years. The Norwegian research vessel GeoSARS launched an expedition in 2005. Scientist Rolf Pedersen directed the complex multidisciplinary marine research team. They surveyed the Måns Ridge near the remote Jan Mayen Island. This specific ridge connects the Icelandic system to the Arctic Ocean. The ship utilized a highly sophisticated autonomous underwater survey vehicle. The AUV mapped the seafloor with completely unprecedented topological detail. It flew exactly 50 meters above the jagged volcanic rocks. The onboard sensors detected massive chemical anomalies in the water. High turbidity readings indicated heavily suspended mineral particles floating nearby. The team deployed a deep-towed camera system to investigate further. At a depth of 500 meters, they found another vent field. They officially named this relatively shallow site the Troll Wall. The ultimate prize waited deeper along the extensive ridge system. In 2008, Pedersen's team returned with much better diving equipment. They brought a specialized deep-water ROV for this specific mission. The new target area lay at a depth of 2,400 meters. The seafloor topography here was incredibly rugged and highly complex. The ROV navigated carefully through a maze of collapsed lava tubes. The precise chemical sensors guided the pilot toward the source. Suddenly, massive black smoke plumes appeared clearly on the monitors. They had finally discovered the Loki's Castle hydrothermal vent field. This site featured for massive and active black smoker chimneys. The structures vented dark fluids at exactly 320 degrees Celsius. The discovery proved that high-temperature venting extended into the Arctic. It bridged the geological gap between Iceland and remote Svalbard. These discoveries fundamentally changed our understanding of global ocean ridges. The Icelandic mantle plume exerts massive thermal influence over the region. This deep upwelling of hot mantle rock creates excess liquid magma. It pushes the seafloor upward, creating the terrestrial island of Iceland. The thermal anomaly extends far along the adjacent submarine ridge lines. Geologists mapped the crustal thickness using advanced seismic refraction techniques. They found the oceanic crust near the vents was unusually thick. The continuous volcanic activity builds up the ocean floor quite rapidly. This creates a highly fractured and incredibly porous rock matrix. Cold seawater penetrates deep into the crust through these open faults. The water travels down several kilometers toward the active magma chamber. Extreme subterranean heat and pressure alter the water's chemical structure completely. The Tjorn's fracture zone proved especially vital to the geological research. This massive transform fault offsets the mid-ocean ridge quite significantly. It creates a complex network of secondary fissures and deep cracks. Small tectonic earthquakes occur here with remarkable and predictable frequency. Seismologists deployed an array of ocean bottom seismometers in 2006. These instruments recorded thousands of micro-earthquakes over a single year. The seismic data revealed the exact hidden pathways of fluid circulation. The frequent earthquakes keep the subterranean hydrothermal plumbing system completely open. Without tectonic movement, mineral deposits would quickly seal the active vents. The constant shaking fractures the newly formed solid rock formations. This allows the superheated water to find new upward escape routes. The hydrothermal fields migrate slowly along the fault lines over centuries. Later scientific expeditions brought increasingly sophisticated analytical tools to Iceland. In 2011, researchers successfully deployed in-situ underwater mass spectrometers. These devices analyze the vent chemistry directly on the deep seafloor. This prevents pressure changes from altering the collected fluid sample composition. The scientists measured precise dissolved gas concentrations in accurate real-time. They found extraordinary levels of natural abiotic methane gas production. This methane forms through water-rock interactions without any biological input. The specific geological process is scientifically known as serpentinization. Olivine-rich volcanic rocks react with seawater to produce pure hydrogen gas. The hydrogen then combines with carbon dioxide to form simple methane. This incredible discovery had massive implications for the field of astrobiology. The Mid-Atlantic Ridge divides the ocean floor near Iceland. This massive geological boundary stretches across the entire globe. Eurasian and North American tectonic plates meet beneath the waves. These giant crustal fragments pull apart continuously without pause. Tectonic forces tear the heavy ocean floor wide open. Magma rises from the deep mantle to fill the void. This action creates a divergent boundary in the dark ocean. The divergent boundary acts as a massive subterranean heat engine. The spreading rate here is considered relatively slow globally. The plates separate at roughly 2.5 centimeters annually. This matches the exact speed at which human fingernails grow. Slower spreading rates create very distinct geological seafloor features. Fast spreading ridges produce smooth and continuous volcanic topographic rises. Slow spreading ridges generate incredibly deep and rugged rift valleys. Massive fault walls rise sharply on either side of the rift. The Kolbeinsey Ridge lies directly north of the Icelandic mainland. It represents a prime example of a slow-spreading tectonic center. Deep tectonic fissures dominate the harsh seafloor landscape here. Earthquakes frequently shake the underlying basaltic ocean bedrock. Seismic monitors record hundreds of tiny microtremors every single day. These gentle tremors map the movement of subterranean magma pools. Scientists use these acoustic signals to track continuous crustal evolution. The Iceland mantle plume adds intense heat to this system. A mantle plume is an upwelling of abnormally hot rock. It sits directly beneath the active oceanic spreading ridge. This rare geological combination creates excessive deep marine volcanic activity. The crust here is exceptionally thick for an ocean basin. Most oceanic crust measures about 7 kilometers in total thickness. The Icelandic marine crust reaches depths of 30 kilometers easily. This extreme thickness alters the local hydrothermal circulation patterns fundamentally. This intense heat flux sustains the complex deep marine ecosystem. The Iceland mantle plume originates deep within the Earth. Seismic tomography maps this thermal anomaly down toward the core. The core mantle boundary sits almost 3,000 kilometers below us. Hot material ascends through the solid mantle over countless millennia. This rising rock behaves like a slow-moving plastic solid material. It melts only when it reaches the shallow oceanic lithosphere. Decompression melting generates vast quantities of fresh basaltic magma. This liquid magma feeds the submarine ridges with molten rock. The plume center sits squarely beneath the massive Vatnajökull glacier. Its thermal influence extends far into the surrounding ocean basin. The seafloor here is much shallower than typical ocean ridges. Anomalous elevation characterizes the entire northern Icelandic marine topography. Fresh basalt covers the newly formed deep ocean floor completely. Pillow lavas form when hot magma meets freezing Arctic seawater. The rapid cooling creates rounded and bulbous dark rock shapes. Geologists categorize these unique structures as pillow basalt rock formations. These pillow structures stack upon each other like ancient stones. Volcanic glass forms on the outer crust of these pillows. The glassy rind shatters easily under immense deep ocean pressure. Beneath the basalt layer lies a solid foundation of gabbro. Gabbro is a coarse-grained intrusive dark igneous rock type. It forms when magma cools slowly deep underground over centuries. Peridotite exists even deeper within the Earth's upper mantle layer. Tectonic faulting sometimes exposes peridotite to the cold ocean water. This rare exposure triggers a chemical reaction called serpentinization. Serpentinization generates natural heat and produces pure hydrogen gas. Extensional forces create a series of parallel massive fault blocks. These heavy blocks form a graben structure along the ridge. A graben is a depressed block of the Earth's crust. Steep rocky escarpments border the central volcanic rift valley. The valley floor contains the youngest and freshest volcanic eruptions. Sheet flows of flat lava cover large areas of the rift. Fissure eruptions open suddenly along the fractured valley floor. Submarine lava fountains can erupt during major tectonic shifting events. The sudden quenching of lava produces sharp volcanic glass shards. These fragments settle as hyaloclastite sediment on the quiet seafloor. Over time, these sediments cement into solid layered rock formations. Water penetrates deep into the heavily fractured volcanic rocks. Hydrothermal fluids leach essential minerals from the surrounding crustal rocks. The superheated water dissolves heavy iron and magnesium very easily. Copper and zinc enter the hydrothermal solution at great depth. The fluid temperature exceeds 300 degrees Celsius down there. High hydrostatic pressure prevents the boiling of this superheated water. The mineral-rich fluid eventually rises back toward the dark seafloor. It meets cold Arctic seawater measuring near 2 degrees Celsius. Sudden thermal cooling causes dissolved minerals to precipitate out immediately. Hydrothermal alteration changes the original basaltic rock completely over time. Chlorite replaces the primary volcanic minerals during the heating process. Epidote forms in the deepest and hottest subseafloor reaction zones. These secondary minerals record the thermal history of the ocean crust. The hydrothermal fluid chemistry reflects this deep rock interaction perfectly. High concentrations of hydrogen sulfide emerge from the active vents. Dissolved methane also vents continuously into the surrounding ocean water. Chemical sensors detect these dissolved gases from miles away underwater. The carbon dioxide levels are unusually high near the Icelandic coast. Magmatic degassing contributes heavily to this constant carbon dioxide flux. The subseafloor magma chambers release trapped ancient gases continuously. Helium isotope ratios confirm the deep mantle origin of fluids. Helium-3 is a primordial isotope from the Earth's initial formation. Its heavy presence indicates a direct connection to the deep mantle. Pyrite forms shiny golden flecks in the active vent chimneys. Pyrite is commonly known by geologists as natural fool's gold. Chalcopyrite adds valuable copper to the growing complex mineral structures. Sphalerite contributes heavy zinc to the intricate vent chimney matrix. Anhydrite provides a crucial structural framework for the fragile chimneys. Calcium sulfate precipitates rapidly from the naturally heated Arctic seawater. Silica glazes the exterior of the older dormant vent formations. This hard silica coating protects the chimneys from rapid ocean erosion. The Kolbeinsey Ridge segment features extremely tall black smoker chimneys. Fine particles of metallic sulfides create the thick black smoke. Iron sulfides absorb all available light in the hot vent fluid. The chimneys here grow incredibly tall and remain very fragile. The surrounding cold water prevents the chimney structures from melting. Some mineral structures reach 15 meters before eventually collapsing downward. The base of these chimneys consists of massive solid sulfide mounds. These heavy mounds accumulate over thousands of years of active venting. Copper-rich minerals form the dense inner core of the chimneys. Zinc-rich minerals coat the outer surfaces of the towering structures. A steep temperature gradient exists across the thin chimney wall. The inside touches 350 degrees superheated hydrothermal fluids. The outside faces 2-degree freezing Arctic Ocean water currents. This extreme thermal gradient drives complex and rapid mineral zoning. The geological age of these deep structures varies quite significantly. The mid-Atlantic ridge itself formed many millions of years ago. The Kölbeinsee Ridge segment is relatively young in geological terms. It began forming roughly 15 million years ago beneath the waves. Specific hydrothermal fields have much shorter and more chaotic lifespans. The Grimsey hydrothermal field formed roughly 3,000 years ago. Individual vent chimneys grow and collapse over mere decades. A single chimney can reach 10 meters in just 10 years. Mineral deposition rates are incredibly fast at these active sites. Researchers date the vent structures using complex radiometric chemical techniques. Radiocarbon dating cannot measure these ancient inorganic mineral rock formations. Radium and lead isotopes reveal the exact age of precipitated minerals. Some active vents show continuous fluid flow for many centuries. Others clog with solid minerals and die within a few years. Dead chimneys eventually crumble into flat metallic sediment mounds. The Grimsey vent field sits in relatively shallow northern waters. It rests at a precise depth of 400 meters. The water pressure here is 40 times standard atmospheric pressure. The vent fluids reach temperatures of 250 degrees. This specific temperature is right at the boiling point here. Submarine boiling creates a spectacular visual effect on the seafloor. Steam bubbles emerge directly from the rocky seafloor vents. This two-phase fluid dynamic alters the local mineral precipitation rates. Gold concentrates heavily in these shallow boiling hydrothermal vent systems. The research vessel Meteor surveyed this northern area very extensively. Scientists deployed the ROV Victor 6000 for close visual observation. Dr. Sven Petersen led multiple deep dives to the Kölbeinsee Ridge. High-resolution sonar mapped the jagged tectonic fault lines perfectly. The DSV Alvin also explored the deeper southern ridge segments. Alvin retrieved massive sulfide samples for detailed surface laboratory analysis. Geochemists study these samples to understand early planetary geological evolution. The coordinates 66 degrees north mark the main active vent field. The RV Poseidon conducted extensive bathymetric sonar surveys here recently. Multibeam echo sounders mapped the seafloor topography precisely and accurately. The resulting maps show volcanic cones dotting the deep rift valley. The ROV Keel 6000 collected high-definition video of the active vents. Laser scaling devices measured the exact physical dimensions of the chimneys. Titanium syringes captured pristine chemical samples of the hydrothermal fluids. These specialized metallic syringes maintain the extreme deep ocean pressure. This prevents the volatile gases from escaping during the slow ascent. Mass spectrometers analyze the fluid composition on the research ship. Scientists drill into the seafloor to retrieve solid core samples. The ocean drilling program recovered deep cores from the ridge flanks. These cylindrical rock samples reveal hidden layers of ancient oceanic crust. Veins of pure quartz cut through the heavily altered basalt. Sulfide minerals fill the microscopic fractures in the solid rock. The geological clock ticks very slowly in the deep ocean. The Kölbeinsee Ridge stretches north from the Icelandic mainland. Tectonic plates pull apart along this submerged volcanic boundary. Fissures open directly into the basaltic crust below. Superheated fluids rise rapidly through these deep geological fractures. Massive hydrothermal structures emerge from the barren seafloor. Scientists call these towering formations hydrothermal vent chimneys. They resemble industrial smokestacks rising from a submerged factory. ROV Victor 6000 mapped this specific field in 2004. High-resolution sonar revealed dozens of distinct mineral spires. Some structures stand completely isolated on the basalt plain. Others form dense clusters across the active fault zone. Black smokers dominate the central region of this field. These chimneys vent dark, mineral-rich fluids into the ocean. The fluid exits the rock at 350 degrees Celsius. Extreme pressure prevents this superheated liquid from boiling. The surrounding seawater remains at a frigid 2 degrees. This massive temperature gradient drives immediate chemical reactions. Dissolved metals precipitate out of the fluid instantly. Tiny particles of metal sulfide form a dark cloud. This phenomenon creates the visual illusion of thick smoke. Dr. Margaret Tivy analyzed these specific mineral precipitation rates. Her research explains the rapid vertical growth of chimneys. A single black smoker can grow 30 centimeters daily. The outer walls consist primarily of porous anhydrite minerals. Calcium and sulfate combine to build this fragile framework. Hot fluids continue flowing upward through the central conduit. Copper and iron sulfides coat the inside of the pipe. These inner layers harden and strengthen the chimney structure. Chalcopyrite forms a distinctive golden lining within the vent. Zinc sulfide adds layers of gray sphalerite to the walls. The chimney walls gradually thicken over several active months. Fluid velocity inside the pipe can exceed 1 meter per second. This rapid flow prevents the central channel from clogging. The primary black smoker here reaches 15 meters high. Geologists named this massive structure the Troll Wall. Its base spans nearly 4 meters in total diameter. Multiple secondary vents branch off from the main trunk. These side channels create a complex plumbing system. The ROV temperature probe recorded 385 degrees at the main orifice. This represents one of the hottest vents near Iceland. Thermal sensors detected fluctuations in the output temperature. These variations indicate tidal influences on the fluid flow. Subsurface magma chambers provide the constant heat source. The magma resides just 2 kilometers beneath the seafloor. Chemical analysis reveals highly acidic vent fluids here. The pH level hovers around 2.8 at the exit point. This acidity matches the strength of common household vinegar. Hydrogen sulfide constitutes a major component of the emission. This toxic gas provides energy for specialized local bacteria. Methane and hydrogen gas also bubble from the chimney. These volatile compounds originate from deep rock interactions. Olivine minerals in the basalt react with heated seawater. This specific process is known scientifically as marine serpentinization. It releases massive amounts of hydrogen into the fluid. The resulting chemical cocktail supports unique biological communities. White smokers populate the periphery of the hydrothermal field. These structures emit a pale, milky fluid into the current. Their operating temperatures range from 260 to 300 degrees Celsius. This cooler fluid travels through different geological pathways. The water mixes with cold seawater deep beneath the crust. Many heavy metals precipitate out before reaching the surface. The remaining fluid carries lighter elements like barium and calcium. Silica also remains dissolved in this cooler hydrothermal mixture. These elements form white particles upon hitting the ocean. The resulting chimneys appear pale gray or stark white. They lack the iron sulfides found in black smokers. The Stryton hydrothermal field features spectacular white smoker chimneys. This unique site sits in Eyjafjörður Bay in northern Iceland. These unique hydrothermal vents operate at remarkably shallow depths. The main chimney peaks just 15 meters below the surface. It grows from a base depth of 65 meters. This makes it the tallest known shallow water chimney. Fresh water from glacial runoff mixes with the vent fluids. This unique hydrology creates a different chemical signature. Magnesium silicate forms the primary building block here. The mineral precipitates slowly over thousands of years. Geologist Erlendur Bogason discovered this towering structure in 1997. The Stryton chimney releases 100 liters of water per second. This fluid maintains a steady temperature of 72 degrees Celsius. It lacks the extreme heat of deep ocean black smokers. However, the underlying structural mechanics remain remarkably similar here. Minerals deposit continuously around the rim of the vent. The chimney grows upward by several centimeters each year. Its porous walls allow warm fluid to seep outward. This creates a thermal halo around the entire structure. Divers frequently measure the temperature gradients along the spire. The rock feels noticeably warm to the human touch. Mineral samples show high concentrations of dissolved silica. Deep-sea chimneys face constant threats of structural failure. The towering mineral spires become incredibly top-heavy over time. Ocean currents exert steady lateral pressure on the formations. Seismic activity regularly shakes the unstable basaltic foundation. A minor earthquake can topple a 15-meter chimney instantly. The collapsed debris forms a large mound of sulfide rubble. Scientists call these accumulated mineral deposits basal mounds. New chimneys quickly begin growing from the fresh wreckage. The hydrothermal fluid simply finds a new path upward. This cycle of growth and destruction continues indefinitely. Some massive sulfide mounds measure 50 meters across. The Jan Mayen vent field lies further north along the ridge. Norwegian researchers successfully discovered this remote site in 2005. The ROV Bathysaurus captured the first visual evidence. This field sits at a depth of 700 meters. It contains some of the largest known black smokers. The Soria Moria chimney complex dominates the local landscape. Multiple spires merge to form a massive sulfide cathedral. The central tower reaches 20 meters above the seafloor. Fluid exits through dozens of small, interconnected nozzles. This diffuses the flow and creates a wide thermal plume. The plume rises hundreds of meters into the water column. Oceanographers track these hydrothermal plumes using chemical sensors. They measure slight anomalies in water temperature and clarity. A nephelometer detects the tiny suspended mineral particles. These particles scatter light from the instrument's laser beam. Manganese concentrations also spike within the dispersing plume. This chemical signature persists for kilometers down the current. Scientists map these signals to locate undiscovered vent fields. The DSV Alvin relies on such data for targeted dives. Precision navigation brings the submarine directly to the chimneys. Titanium sampling bottles collect pure hydrothermal fluid from the source. These pressurized containers prevent dissolved gases from escaping. The chimneys exhibit distinct zoning in their mineral composition. The hottest central core consists of pure chalcopyrite. This copper iron sulfide requires temperatures above 300 degrees to precipitate. Moving outward, the temperature drops rapidly through the chimney wall. The middle layer contains primarily zinc sulfide and pyrite. The outermost shell remains in contact with freezing seawater. This cold exterior consists of amorphous silica and barite. This concentric layering records the thermal history of the vent. Geochemists slice recovered chimney samples into thin cross-sections. Microscopic analysis reveals the sequence of mineral deposition. These rings resemble the growth patterns found in ancient trees. Some vents feature unique flange structures on their sides. These horizontal ledges trap pools of superheated fluid underneath. The trapped water reflects the ROV lights like a mirror. This creates an upside-down pool of shimmering hot fluid. The water slowly spills over the edge of the flange. It flows upward along the side of the main chimney. Minerals precipitate along the lip of the overhang. This causes the flange to grow steadily outward. Some ledges extend 2 meters from the central spire. They create sheltered microenvironments protected from ocean currents. Temperature gradients across a flange are incredibly steep. The Grimsey hydrothermal field provides another Icelandic example. This site sits just north of the Arctic Circle. It occupies a shallow shelf roughly 400 meters deep. The vents here produce mostly clear, shimmering fluid. This indicates a lower concentration of dissolved heavy metals. The chimneys consist largely of white anhydrite and silica. They rarely exceed 3 meters in total height. The underlying rock contains thick layers of oceanic sediment. The hydrothermal fluid filters through this mud before erupting. This filtration process removes many of the darker minerals. The resulting chimneys appear incredibly fragile and delicate. Hydrothermal fluid composition changes as the volcanic system ages. A newly opened fissure vents extremely hot, metal-rich water. Massive black smokers form rapidly during this initial phase. Over decades, the underlying magma chamber gradually cools. The fluid temperature drops below 300 degrees Celsius. The black smokers slowly transition into cooler white smokers. Eventually, the heat source moves or dissipates entirely. The chimney stops venting and becomes completely dormant. Cold seawater slowly dissolves the outer anhydrite layers. The exposed sulfide core remains standing for centuries. These inactive chimneys slowly oxidize in the deep ocean. Dr. Robert Ballard pioneered the study of these structures. His early expeditions revealed the complexity of vent geology. Modern ROVs now capture millimeter-scale laser scans of chimneys. This creates precise three-dimensional models of the entire field. Scientists use these models to calculate total mineral volume. The Troll Wall complex contains an estimated 50 tons of sulfides. This represents a massive concentration of valuable industrial metals. Copper, zinc, and gold accumulate in these deep-sea deposits. The extreme pressure alters the crystalline structure of the minerals. This forms uniquely dense ores not found on dry land. The geological processes operate at highly accelerated rates. A chimney's internal plumbing can shift without warning. Mineral precipitation naturally constricts the central flow channel. The fluid pressure builds up behind the blockage. The fluid composition here challenges traditional marine chemistry. These northern vents release a highly unusual chemical mixture. Scientists measure dissolved gases to understand the volcanic plumbing. The chemical signature reveals processes hidden beneath the crust. Each vent field displays a distinct molecular fingerprint. Researchers from the University of Iceland map these anomalies. They use specialized titanium syringes to capture pristine fluids. The samples must remain pressurized during the long ascent. This prevents dissolved gases from escaping into the atmosphere. Laboratory analysis reveals unexpected concentrations of rare earth elements. The chemical profile differs drastically from typical oceanic ridges. Shallow depth allows meteoric groundwater to mix with seawater. This creates a complex hybrid hydrothermal fluid system. The resulting chemistry drives unique biological and geological processes. Most global hydrothermal vents emit highly acidic fluid streams. Those typical black smokers usually register a pH around 3. The Iceland vents present a completely different pH reality. The Triton field features an incredibly high alkaline environment. Sensors on the ROV Victor 6000 measure a pH of 10. This extreme alkalinity resembles household bleach or ammonia solutions. Such basic conditions are rare in the global ocean. The high pH results from reactions with magnesium-rich rocks. Freshwater runoff from Icelandic glacier influences this basic chemistry. The glacial meltwater percolates through porous basaltic crust. It loses magnesium and sulfate during this underground journey. The fluid emerges highly enriched in dissolved silica compounds. When this basic fluid meets neutral seawater, minerals precipitate. This alkaline reaction builds the massive smectite clay chimneys. Other nearby fields on the Kolbeinsey Ridge remain slightly acidic. This proximity of contrasting pH levels fascinates marine geologists. Salinity measurements provide clues about the fluid origins. Standard ocean water contains roughly 35 parts per thousand. The hydrothermal fluids at Triton show remarkably low salinity. Instruments record values as low as 5 parts per thousand. This indicates a massive influx of terrestrial fresh water. Glacial runoff travels miles beneath the coastal sea floor. It mixes with oceanic water within the heated crust. This low salinity creates a buoyant hydrothermal plume. The lighter fresh water rises rapidly through the dense ocean. Scientists track this salinity gradient using conductivity sensors. The RV Meteor deployed these sensors during a summer expedition. Data logs show sharp drops in salt concentration near vents. Further offshore, the Grimsey vent field shows normal marine salinity. There, the fluids consist entirely of recycled ocean water. The contrast in salinity affects local mineral deposition rates. Low salinity fluids carry different metal isotopes to the surface. Hydrogen sulfide acts as the primary energy source for vent ecosystems. This toxic gas smells like rotten eggs at the surface. Deep pressure keeps the hydrogen sulfide dissolved in solution. Typical mid-ocean ridges output roughly 10 millimoles per liter. The Iceland vents show much lower sulfide concentrations. Measurements indicate only 2 to 3 millimoles per liter. Dr. Sven Petersen analyzed these sulfide levels in 2000. He noted the low sulfur content in the host basalt. The Icelandic crust contains fewer sulfide minerals than older crust. Less sulfur in the rock means less gas in the fluid. This reduced sulfide availability limits the growth of certain bacteria. It explains the absence of giant tube worms here. Instead, different microbial mats adapt to the lower sulfide levels. The fluid also contains traces of dissolved iron sulfides. These iron compounds oxidize rapidly upon contacting cold seawater. This oxidation creates faint yellow clouds around the vent orifices. Methane gas provides another crucial chemical energy source. The Kolbeinsey Ridge vents emit surprisingly high methane volumes. Spectrometers measure methane at 50 micromoles per liter. This concentration is 10 times higher than typical basaltic vents. Dr. Marvin Lilly studied these methane anomalies extensively. He used the submersible Alvin to collect gas samples. The high methane suggests unique subsea floor chemical reactions. Carbon dioxide reacts with hydrogen gas in the crust. This abiotic process generates methane without biological involvement. The reaction requires specific iron-rich olivine minerals to occur. Icelandic basalt contains abundant olivine crystals in its matrix. The heated water alters the olivine into serpentine rock. This serpentinization process releases large amounts of hydrogen gas. The hydrogen then binds with carbon to form methane. This chemical pathway mirrors conditions on the early Earth. It offers clues about the origin of terrestrial life. Chemical isotopes reveal the precise age of the hydrothermal fluids. Scientists measure the ratio of oxygen-18 to oxygen-16. The fluids show a distinct depletion in heavy oxygen isotopes. This isotopic signature confirms the presence of ancient glacial ice. The water circulating through the crust fell as snow millennia ago. Helium isotopes provide information about deep mantle degassing. The ratio of helium-3 to helium-4 is unusually high. This indicates a direct connection to the deep mantle plume. The Iceland hotspot delivers primordial helium directly to the surface. Researchers use mass spectrometers to calculate these precise ratios. The equipment detects variations as small as 1 part per million. Carbon isotopes in the methane also point to an inorganic origin. Biological methane contains more of the lighter carbon-12 isotope. The vent methane contains heavier carbon-13 isotopes. This confirms the gas forms through geological rock reactions. The chemical profile shares traits with the Lost City field. Lost City sits far south on the Mid-Atlantic Ridge. Both locations feature highly alkaline fluids and giant carbonate structures. However, Lost City fluids reach a maximum temperature of 90 degrees. The Icelandic alkaline vents barely exceed 70 degrees Celsius. Lost City rests on exposed mantled rock called peridotite. The Iceland vents sit on thick layers of basaltic lava. This difference in host rock alters the secondary trace elements. Lost City fluids contain almost no dissolved silica compounds. The Striton fluids carry massive loads of dissolved silica. This silica creates smectite clays instead of calcium carbonate chimneys. Both fields produce significant amounts of abiotic methane gas. They demonstrate how different rocks produce similar alkaline environments. Marine chemists study both to understand global hydrothermal diversity. Pacific vents like Juan de Fuca present a contrasting chemistry. The Pacific fluids are highly acidic and rich in metals. They carry massive concentrations of iron, zinc, and copper. The Icelandic fluids contain very few dissolved heavy metals. The low metal content results from the shallow water pressure. Water boils at lower temperatures in the shallow Northern Ocean. Boiling separates the fluid into a vapor and a brine phase. Only the metal pore vapor phase escapes from the seafloor. This explains the lack of massive sulfide deposits in Iceland. Pacific vents build towering structures of solid metal sulfides. The Icelandic vents build fragile structures of silica and clay. Pacific fluids reach temperatures exceeding 300 degrees Celsius. The Icelandic vapor phase cools significantly before venting. Carbon dioxide levels in these northern vents are extraordinary. The magma beneath Iceland contains high levels of volatile gases. These gases transfer into the circulating hydrothermal fluids. Sensors measure carbon dioxide at 200 millimoles per liter. This creates localized pools of high acidity near some vents. The dissolved gas forms microscopic bubbles in the water column. ROV cameras capture these bubbles rising from the sediment. The bubbles dissolve completely before reaching the ocean surface. This massive carbon input supports specialized chemosynthetic bacteria. The bacteria fix the inorganic carbon into organic molecules. Dr. Richard Harrington mapped these carbon fluxes in detail. He calculated the total carbon output of the Kolbeinsey Ridge. The ridge contributes significantly to the regional carbon cycle. The high carbon dioxide also accelerates the weathering of local basalts. Trace elements provide a microscopic view of crustal interactions. The fluids contain measurable amounts of lithium and boron. Lithium concentrations consistently reach 50 micromoles per liter here. This alkali metal leaches easily from the hot volcanic rock. Boron isotopes help scientists trace the fluid circulation pathways. The fluids also carry rare earth elements like europium. Europium anomalies serve as a thermometer for deep fluid reactions. A positive europium anomaly indicates temperatures previously exceeded 200 degrees. The current vent temperatures may only register at 70 degrees. The europium proves the fluid was much hotter in the past. It cooled while ascending through the fractured crustal rocks. Scientists use inductively coupled plasma mass spectrometry for these measurements. This technique detects elements at parts per trillion levels. Nitrogen compounds add another layer of chemical complexity. Deep ocean water naturally contains dissolved nitrate molecules. The intense heat and pressure strip oxygen from the nitrogen. Ammonia concentrations at Striton reach 20 micromoles per liter. This ammonia provides essential nitrogen for biological protein synthesis. Microorganisms utilize the ammonia to build cellular structures. Magnesium behaves uniquely in these high-temperature marine environments. Normal seawater contains roughly 53 millimoles of magnesium. The hydrothermal fluids emerge with exactly zero dissolved magnesium. This complete depletion is a hallmark of hydrothermal circulation. As cold seawater enters the crust, it heats up rapidly. It forms new clay minerals within the basaltic crust. This process releases hydrogen ions into the circulating fluid. These hydrogen ions usually make the resulting fluid highly acidic. The fresh water dilutes the hydrogen ions before they reach the surface. Calcium concentrations increase significantly during the fluid circulation process. The hot acidic water dissolves calcium from the host rock. The fluid emerges with double the calcium of normal seawater. This dissolved calcium reacts with sulfate in the cold ocean. Anhydrite dissolves easily when the vent fluid temperatures drop. The hydrothermal fluids are completely devoid of dissolved oxygen. They represent a highly reducing, extreme chemical environment. The instrument readings show strongly negative millivolt values. This indicates a strong tendency to donate electrons. When this reducing fluid meets oxygen-rich seawater, reactions occur rapidly. The Kolbeinsey Ridge stretches directly north of the Icelandic coast. This underwater volcanic fracture hosts highly unique biological communities. Warm hydrothermal fluids support incredibly dense biological populations here. The biological makeup differs entirely from southern vent systems. Giant tube worms and large clams are completely absent here. Instead, a radically different ecosystem thrives in the darkness. Life depends entirely on chemical energy from the Earth. Microbes form the absolute foundation of this deep food web. They process toxic hydrogen sulfide from the venting fluids. The resulting organic matter sustains the entire local animal population. Extensive microbial mats cover the surrounding black basalt rocks. These biological mats consist primarily of Beggiatoa bacterial strains. The bacterial filaments create thick white carpets across the seafloor. Some continuous mat areas span several square meters in size. The dense microbial layer reaches 3 centimeters in total thickness. Bacterial biomass frequently exceeds 50 grams per square meter. Scientists from the Max Planck Institute studied these extensive mats. Dr. Antje Betius analyzed their complex internal metabolic pathways. These microbes utilize sulfur oxidation for their cellular energy production. They fix dissolved carbon dioxide directly into usable organic carbon. The bacterial filaments exhibit a specialized gliding movement mechanism. They actively adjust their position within the steep chemical gradient. Optimal bacterial growth occurs at exactly 70 degrees Celsius. The bacteria store pure elemental sulfur within their microscopic cells. These internal sulfur granules reflect light from the submersible vehicles. ROV Victor 6000 recorded high-resolution images of these bacterial mats. The bright white patches contrast sharply with dark volcanic rock. Another bacterium called Thiothrix attaches directly to the vent chimneys. These attached microbes form long flowing streamers in the water. The biological streamers sway constantly in the warm hydrothermal currents. Small marine crustaceans graze heavily on these thick bacterial mats. The amphipod Bouviarella curtirama completely dominates this specific ecosystem. This unique species is strictly endemic to the Icelandic vents. You will not find them anywhere else on our planet. They possess specialized mouthparts for effectively scraping the bacteria. Their localized population densities are incredibly high in this region. Researchers count up to 10,000 individuals per square meter. They form incredibly dense swarms around the warm fluid exits. These amphipods prefer water temperatures around exactly 15 degrees Celsius. They carefully avoid the boiling fluids of the main chimneys. Bouviarella curtirama measures only 5 mm in total body length. Their tiny bodies lack any pigment in this lightless environment. They rely entirely on chemical sensors to navigate the vents. Delicate antennae detect minute trace amounts of dissolved hydrogen sulfide. This sensory ability helps them locate fresh bacterial growth zones. These active amphipods reproduce continuously throughout the entire calendar year. Females carry developing embryos inside a specialized ventral brood pouch. This anatomical feature ensures high survival rates for the offspring. The constant chemical food supply supports rapid population turnover rates. Secondary biological production rates are exceptionally high in this habitat. Tiny marine snails share these productive bacterial grazing grounds. Pseudocetia greigi is a prominent endemic gastropod in this region. Their incredibly fragile shells measure just 2 mm across. These snails congregate safely in the cooler peripheral vent zones. The submersible Jago collected numerous specimens during a 1988 expedition. Marine biologist Hans Frick documented their specific spatial distribution patterns. The snails achieve maximum densities of 4,000 per square meter. They use a tiny viewer to scrape microbes from rocks. Their calcium shells exhibit highly unique carbon isotopic signatures. These chemical signatures confirm their strict reliance on chemosynthetic food. The calcium carbonate shells of these snails are unusually thin. Deep ocean acidity normally dissolves thick calcium structures very quickly. The snails compensate with a highly specialized protective protein layer. This periostracum shields the delicate shell from corrosive vent fluids. Extensive genetic studies reveal their total isolation from other populations. Ocean currents rarely transport their microscopic larvae across long distances. They remain strictly confined to the Kolbeinsey Ridge volcanic system. The total habitable area covers less than 1 square kilometer. This extreme localization makes the species highly vulnerable to changes. A single massive volcanic eruption could alter their entire habitat. Aggressive predators constantly patrol the edges of the microbial mats. Pollinoid polychaetes are the primary invertebrate hunters in this zone. Hamarthoglobifera is a surprisingly large predatory scale worm species. These segmented worms reach up to 5 centimeters in length. They possess incredibly powerful jaws for capturing the grazing amphipods. Overlapping dorsal scales protect their upper surface from the heat. Sensory tentacles detect the subtle water vibrations of moving prey. The scale worms naturally maintain much lower overall population densities. Scientists record only about 50 individual worms per square meter. They represent the absolute top of this highly localized food chain. Smaller bristle worms inhabit the numerous dark sediment crevices. Capitellid worms burrow deeply into the chemically altered volcanic mud. They constantly ingest the sediment to extract trapped organic matter. Their specialized digestive systems process the decaying bacterial remains. These worms tolerate incredibly high concentrations of dissolved heavy metals. Local vent fluids contain highly toxic levels of copper and zinc. Specialized proteins in their blood bind directly to these metals. This internal detoxification mechanism allows survival in extremely harsh conditions. The constant burrowing activity naturally oxygenates the upper sediment layers. This vital process supports a diverse community of subsurface microbes. Total faunal biomass averages exactly 200 grams per square meter. This specific figure is significantly lower than mid-Atlantic ridge vents. Tropical vent systems often exceed several kilograms per square meter. However, the Icelandic vent fields remain a vital Arctic oasis. The surrounding deep ocean floor is virtually barren of life. Away from the vents, biomass drops to mere milligrams. The hydrothermal energy creates a completely isolated biological hotspot. Organic carbon production rivals highly productive coastal surface waters. The entire ecosystem operates completely independently of solar energy inputs. Nutrient recycling occurs at an incredibly rapid pace right here. Sea anemones successfully colonize the much cooler basalt rock margins. Urticina felina attaches firmly to the hard volcanic rock substrate. These specific anemones do not rely on internal chemosynthetic bacteria. They are active suspension feeders capturing drifting organic matter. The vent currents carry loose bacterial clumps into the water. The anemones use potent stinging tentacles to catch these particles. They essentially form a living biological filter around the vent field. Their population density reaches 20 individual anemones per square meter. They thrive perfectly in waters between 2 and 5 degrees Celsius. The large anemones provide crucial habitat for smaller marine organisms. Intricate glass sponges also populate the distant vent periphery zones. Cladorhiza gelida is a highly unusual carnivorous deep-sea sponge. It captures tiny swimming crustaceans with sharp hook-like silica spicules. This sponge adapts perfectly to the nutrient-poor Arctic Ocean waters. The proximity to the vent significantly increases their prey encounters. Thermal fluid circulation draws deep ocean water toward the chimneys. This induced current brings drifting plankton directly into the sponge colonies. ROV Dives in 2004 documented these extensive peripheral sponge grounds. The sponges stabilize the loose volcanic sediment with their root systems. They add vital structural complexity to the flat black basalt plains. The Grimsey vent field lies much closer to the Icelandic coast. Precise coordinates place it at 66 degrees 36 minutes north. The biological community here faces entirely different environmental pressures. The surrounding water depth measures only 90 meters in total. Photosynthetic life occasionally interacts with this shallow chemosynthetic community. However, the vent endemic species still dominate the immediate area. Thick bacterial mats cover the shallow hydrothermal mineral mounds. The microbial mats actively compete with marine algae for space. This ongoing competition creates a highly rare overlapping ecological zone. Sunlight faintly penetrates through the uppermost layers of the ocean. At the Grimsey field, the hydrostatic pressure is much lower. The physical boiling point of seawater is significantly reduced here. Fluids exit the cracked seafloor at roughly 200 degrees Celsius. The thermal temperature gradients are extremely steep in this location. Thermophilic bacteria perfectly adapt to these incredibly rapid temperature shifts. Pyrococcus furiosus is a highly notable archaean found living here. This extreme microbe multiplies rapidly at exactly 100 degrees Celsius. Its cellular enzymes remain completely stable at these extreme temperatures. Biotechnology companies actively study these specific enzymes for industrial applications. The extracted genetic material offers deep insights into early life evolution. Microscopic animals thrive deep within the thick bacterial mats. Marine nematodes represent the most abundant myofauna at these vents. Oncholamus campylocircoides is a highly dominant nematode species found here. Thousands of these tiny roundworms occupy a single cubic centimeter. They constantly wriggle through the dense matrix of bacterial filaments. The nematodes feed actively on the bacteria and single-celled organisms. Their transparent bodies measure less than 1 single millimeter in length. They easily tolerate extremely low oxygen levels inside the bacterial mats. Their reproductive cycles are closely tied to hydrothermal fluid flow fluctuations. They can survive brief environmental periods of complete oxygen deprivation. Harpacticoid copepods share this microscopic habitat with the numerous nematodes. Ameiera parasitica is frequently found within the Kolbeinsey sediment samples. These tiny crustaceans possess specialized appendages for grasping slippery filaments. They navigate the steep chemical gradients with truly remarkable precision. Scientists use specialized sediment cores to study their microscopic distribution. A 1999 RV meteor expedition collected highly extensive core samples. Dr. Sabine Gollner meticulously analyzed the complex myofauna community structures. The sheer diversity of microscopic life completely surprised the research team. Over 50 entirely new species were identified from these specific samples. This microscopic diversity highlights the hidden complexity of the ecosystem. The entire vent ecosystem relies on incredibly precise chemical balances. The Iceland vent ecosystem operates entirely without sunlight. Geothermal energy replaces solar radiation in this cold environment. Arctic bottom waters maintain a constant freezing temperature. Hydrothermal fluids provide localized pockets of extreme heat. This stark thermal contrast defines the local biological habitat. Organisms here evolved under highly specialized physical conditions. Shallow depths distinguish these fields from mid-ocean ridges. Many active vents sit just 50 meters below the surface. Others extend down to 400 meters deep. Pressure levels here remain significantly lower than abyssal plains. Lower pressure affects how dissolved gases behave underwater. Carbon dioxide and hydrogen sulfide bubble continuously upward. These chemical compounds form the fundamental basis of life. Marine biologists study this specific chemical energy transfer closely. Chemosynthesis drives the entire biological network near Iceland. Microbes extract energy from inorganic mineral compounds directly. Hydrogen sulfide serves as the primary electron donor. Bacteria oxidize this toxic gas to produce cellular energy. This microscopic process fixes dissolved carbon into organic molecules. The chemical reaction yields simple sugars for biological growth. Sulfur oxidizing bacteria thrive in the warm fluid mixing zones. Filamentous strains like Beggiatoa create thick white microbial mats. These biological mats cover the basaltic rock surfaces completely. They resemble fresh snowfall across the dark volcanic seafloor. Some mats reach several centimeters in total physical thickness. Millions of single-celled organisms pack into every square millimeter. Archaea dominate the hotter regions near the vent chimneys. These extremophiles tolerate temperatures exceeding 80 degrees Celsius. Their specific enzymes remain stable under intense thermal stress. Iron oxidation provides another crucial energy pathway here. Zetaproteobacteria specialize in consuming dissolved iron from the crust. They excrete solid iron oxide as a metabolic byproduct. This biological waste forms intricate rust-colored mineral structures. Methane gas also escapes from the fractured ocean floor. Methanotrophic bacteria consume this potent greenhouse gas very efficiently. They prevent massive methane releases into the upper ocean. These microbes convert methane carbon directly into microbial biomass. Dr. Antje Betius documented these methane-consuming communities extensively. A research team mapped the biological gas filters thoroughly. They used the ROV Victor 6000 for precise sampling. Sensors measured methane concentrations across the entire vent field. The acoustic data revealed high efficiency in gas consumption. Energy flows continuously from Earth's mantle into living cells. The thick microbial mats support a diverse grazing community. Tiny gastropods scrape the bacteria from the rocky substrate. These sea snails possess specialized doulas for continuous feeding. Their fragile shells show adaptations to the acidic waters. Amphipods swarm around the warm fluid discharges constantly. These small crustaceans consume loose bacterial clumps directly. They navigate the sharp thermal gradients with remarkable precision. Water temperatures fluctuate wildly within mere millimeters here. Amphipods avoid the boiling fluids while grazing safely nearby. Nematode worms burrow deeply into the thick bacterial mats. They consume dead microbial cells and recycled organic matter. This grazing activity stimulates further bacterial growth cycles rapidly. The primary consumers transform microbial biomass into animal protein. They represent the second critical trophic level found here. Predators patrol the outer edges of the active vents. Zooarcid fish navigate the murky, mineral-rich water columns. These bottom-dwelling eelpouts hunt the grazing amphipods and snails. Their slow metabolism suits the cold ambient Arctic water. They dart quickly into the warm zones only to feed. Sea spiders crawl slowly over the jagged basalt rocks. These pycnogonids extract fluids from soft-bodied invertebrate prey items. Predatory sea anemones anchor themselves to inactive chimney structures. Their stinging tentacles capture drifting organic matter and crustaceans. Dr. Stefan Leth Jorgensen analyzed these specific predator-prey interactions. His scientific team deployed baited traps near the bases. Camera systems recorded feeding behaviors over 48-hour periods. The digital footage revealed a highly structured local food web. Energy moves efficiently from microscopic bacteria to apex predators. This ecosystem differs vastly from Pacific hydrothermal vent fields. The famous giant tube worms are completely absent here. Rifsha pachyptela cannot survive in these specific Arctic conditions. Pacific vents rely heavily on internal endosymbiotic biological relationships. Icelandic vents feature mostly free-living external bacterial mats. Pacific vent clams and large mussels are also missing entirely. The geographic isolation of the Arctic Ocean creates biological barriers. Larval dispersal from the distant Pacific remains physically impossible. The shallow depth also changes the biological community structure. Deep Pacific vents experience pressures of 300 atmospheres. Icelandic shallow vents experience only 10 to 40 atmospheres. This lower pressure allows different physiological adaptations to emerge. The faunal composition reflects this distinct evolutionary history perfectly. Endemic Arctic species dominate the local vent biology completely. Comparisons with the deep mid-Atlantic ridge provide further insights. The Tag hydrothermal field sits thousands of meters deeper. Tag hosts massive swarms of specialized blind vent shrimp. Rimicaris exoculator dominates the mid-Atlantic biological landscape completely. These specific shrimp do not inhabit the shallow Icelandic fields. Instead, coastal Arctic species adapted to the hydrothermal environment. Common coldwater sea stars forage near the vent periphery. They exploit the abundant biological food source migrating outward. The Lost City hydrothermal field offers another scientific comparison. Lost City features highly alkaline fluids and carbonate chimneys. Icelandic vents generally emit acidic fluids rich in dissolved silica. This chemical difference drastically alters the microbial foundation entirely. Silicate structures support entirely different strains of localized archaea. The ecosystem architecture depends strictly on the underlying geology. Some localized symbiotic relationships do exist near northern Iceland. Certain deep sponges host methanotrophic bacteria within their tissues. The bacteria provide fixed carbon directly to the sponge. The sponge offers a stable habitat in turbulent bottom currents. This mutualism mirrors deep ocean adaptations on a smaller scale. Researchers discovered these sponges near the active Kolbeinsey Ridge. The exact coordinates read 67 degrees north, 18 degrees west. Depths there reach 110 meters below. The submersible Jago collected the first biological samples there. Scientists carefully analyzed the sponge tissues in sterile laboratories. Isotope analysis confirmed the biological carbon transfer process definitively. Carbon-13 ratios matched the local geological methane signatures perfectly. This chemical matching proved the chemosynthetic origin of the tissue. Such discoveries highlight the incredible adaptability of marine organisms. The overall biomass density here remains incredibly high. Vent communities produce thousands of times more organic material. This contrasts sharply with the barren surrounding Arctic seafloor. The deep abyssal plains rely on falling debris from above. Marine snow provides a very limited caloric input normally. Vent ecosystems generate their own independent food supply constantly. They function as isolated biological oases in the cold darkness. Currents distribute some excess organic matter to neighboring regions. Filter feeders position themselves perfectly along these outgoing currents. They capture escaping bacteria before they reach freezing open waters. This nutrient export enriches the wider regional marine environment. The geological heat source sustains this entire biological engine. If a vent stops flowing, the local ecosystem collapses rapidly. The thick microbial mats dissolve within a few short weeks. Scavengers quickly consume the remaining animal biomass completely. Icelandic hydrothermal systems exhibit remarkable long-term environmental stability. The Stryton vent field has remained active for millennia. Carbon dating of the massive silicate chimneys confirms their age. Some towering structures formed over 11,000 years ago. This longevity allows complex ecological relationships to develop fully. Generations of organisms adapt precisely to their distinct chemical niches. The steady flow of nutrients prevents sudden population crashes. Seasonal changes on the ocean surface have no direct impact. Winter ice cover does not reduce the biological productivity below. The chemosynthetic engine runs continuously without any seasonal interruptions. Scientists monitor these sites using autonomous underwater vehicles regularly. The AUV*X map the biological distribution patterns precisely. Acoustic sensors measured the exact spatial volume of the biomass. The collected data showed stable population densities across multiple years. Different zones around the vents host distinct microhabitats. The central fluid discharge channels contain extreme hyperthermophilic archaea. Temperatures here often exceed 100 degrees Celsius easily. Just millimeters away, the surrounding water cools to 50 degrees. Thermophilic bacteria dominate this slightly cooler transitional fluid zone. The outer porous chimney walls maintain a mild 20 degrees. This specific temperature band supports the densest animal populations. Amphipods and tiny snails crowd into this narrow thermal corridor. The ambient seawater sits constantly at a frigid 2 degrees. Peripheral scavengers wait patiently in this cold outer boundary. This steep thermal gradient creates distinct biological zoning patterns. Marine ecologists map these zones to understand species distribution. Each organism occupies a highly specific thermal and chemical range. Competition for optimal positioning remains fierce among the local invertebrates. The ecosystem plays a crucial role in global biogeochemical cycles. Vent bacteria process massive amounts of dissolved marine sulfur. They alter the chemical composition of the surrounding seawater significantly. Ion oxidizing microbes lock heavy metals into solid mineral forms. This biological precipitation prevents toxic metal accumulations locally. The organisms actively shape their own physical environment constantly. Microbial mats trap suspended mineral particles from the water column. This biological trapping mechanism accelerates the growth of the chimneys. Biological activity directly influences local geological formation rates. Geology and biology remain inextricably linked in this natural system. Dr. William Martin studied these specific geobiological interactions deeply. His scientific theories connect vent chemistry to the origins of life. The hydrothermal conditions here mimic the ancient primordial ocean chemistry. Studying these modern vents reveals ancient evolutionary biological pathways. A specific species of gastropod dominates the local grazing community. The physical structure of this snail is highly specialized. Its shell contains trace amounts of precipitated iron sulfide. This metallic incorporation strengthens the shell against crushing fluid pressure. The acidic vent fluids normally dissolve calcium carbonate rapidly. The protective iron coating prevents the acidic water from penetrating. Scientific exploration of the Iceland Vents began decades ago. Early research missions faced severe Arctic weather conditions. Researchers relied on basic sonar mapping techniques initially. The research vessel Poseidon arrived in August 1999. Scientists sought thermal anomalies along the Kolbeinsey Ridge. Dr. Colin Devey led this pioneering scientific expedition. The team deployed simple temperature probes directly overboard. They recorded sudden thermal spikes near the deep seafloor. Water temperatures jumped rapidly from 2 degrees to 20. This sudden change indicated active geothermal venting directly below. The depth measured exactly 400 meters down. Sonar revealed massive chimneys rising from the dark basalt. These early topographic maps provided crucial baseline scientific data. Subsequent years brought advanced submersibles to these northern waters. The manned submersible Jargo conducted several important deep dives. 2 pilots navigated the tiny acrylic pressure sphere carefully. They descended into the freezing Arctic Ocean bottom currents. Visibility remained incredibly poor due to thick marine snow. Jargo eventually reached the Grimsey hydrothermal vent field. The precise geographic coordinates were 66 degrees north. Pilots observed gas bubbles escaping from the sandy bottom. They collected hot fluid samples using mechanical robotic arms. The internal cabin temperature dropped near absolute freezing levels. Researchers wore heavy thermal suits during these long dives. Each hazardous dive lasted approximately 4 to 5 hours. Strict battery limitations restricted their time at the bottom. Technological breakthroughs eventually shifted focus to unmanned robotic vehicles. The ROV Victor 6000 revolutionized Arctic deep-sea marine research. This robotic explorer could remain submerged for several days. A reinforced umbilical cable connected it to the ship. Fiber optic lines transmitted high-definition video instantly to the surface. Scientists watched the live feed from a warm control room. The year was 2004 during a major biological survey. Dr. Antje Betius directed the complex biological sampling program. A dedicated team designed specialized titanium extraction syringes. These unique tools extracted undisturbed fluid from the vents. The titanium metal prevented contamination from the surrounding seawater. Precise chemical analysis became entirely possible for the first time. Victor 6000 carried an impressive array of sensitive instruments. A mass spectrometer analyzed dissolved vent gases in real time. Researchers detected high concentrations of pure methane and hydrogen. The ROV also utilized a multibeam acoustic echo sounder. This advanced device mapped the vent field with millimeter precision. Scientists identified dozens of highly active hydrothermal chimneys. Some towering structures measured over 10 meters in height. The maps revealed complex fracture networks in the crust. Superheated fluid channeled through these specific deep geological faults. The robotic arms carefully collected fragile mineral deposits. Operators on the surface controlled every single micro-movement. Telemetry data flowed continuously up the long fiber optic cable. Expeditions soon moved further north along the volcanic ridge. The search for deeper vents required much heavier equipment. In July 2008, a Norwegian research team made history. Dr. Rolf Pedersen led the ambitious multidisciplinary ocean expedition. They explored the Mons Ridge near the Jan Mayen Island. The research vessel GEO-SARS served as their floating base. They deployed a specialized autonomous underwater vehicle for mapping. The AUV scoured the rocky seafloor at 2,400 meters. It operated entirely without a tether to the surface. Pre-programmed algorithms guided its precise grid-like search pattern. Onboard chemical sensors sniffed for hydrothermal plumes in the dark. The autonomous vehicle returned to the surface after 20 hours. Data downloads quickly revealed a massive hidden hydrothermal system. Scientists named this spectacular new site Loki's Castle. The exact coordinates placed it at 73 degrees north. 5 giant sulfide chimneys dominated the barren underwater landscape. Black mineral smoke billowed violently from the jagged peaks. The ROV Bathysaurus was immediately deployed for visual confirmation. Temperature probes recorded vent fluids at 320 degrees Celsius. This extreme heat existed right beside freezing ambient seawater. The physical pressure at this depth exceeded 240 atmospheres. Standard sampling equipment would instantly crush under these conditions. Engineers had designed pressure-compensated hydraulic systems specifically for this. The historic mission yielded truly unprecedented geological core samples. Biologists aboard the GEO-SARS worked in specialized clean labs. They processed delicate biological samples within minutes of retrieval. Dr. Pedersen focused intently on the unique microbial mats. These specialized bacteria thrived entirely on toxic hydrogen sulfide. Researchers used advanced DNA sequencers right on the ship. They successfully identified entirely new species of deep-sea archaea. The expedition proved that Arctic vents hosted completely isolated ecosystems. Powerful ocean currents around Iceland acted as invisible physical barriers. Biological larvae could not easily migrate to other ocean ridges. This extreme isolation sparked rapid and unique evolutionary divergence. The 2008 expedition published their groundbreaking findings in major journals. It fundamentally changed existing deep-sea biological paradigms forever. Long-term monitoring programs began taking shape shortly after discovery. Brief summer expeditions provided only limited snapshot observational data. Scientists desperately needed continuous observations throughout the harsh winter. The surface ocean freezes completely over for several months. Research ships cannot safely access these coordinates during that time. In September 2015, a brilliant new strategy was implemented. The German research vessel Meteor visited the Kolbeinsee Ridge. The team deployed 3 permanent autonomous seafloor monitoring observatories. Heavy concrete anchors held the titanium platforms firmly in place. Each unit carried an advanced acoustic Doppler current profiler. These instruments accurately measured the flow rate of the plumes. High-capacity lithium battery packs powered the scientific instruments continuously. The observatories included highly sensitive broadband seismic monitoring sensors. These detected tiny micro-earthquakes deep within the oceanic crust. Subterranean magma movement generates very distinct acoustic wave signatures. Researchers wanted to correlate seismic activity with vent temperature changes. A network of specialized thermistors was placed directly into vents. They recorded minor temperature fluctuations every 10 minutes exactly. The valuable data logged safely onto waterproof solid-state drives. Acoustic modems allowed limited wireless data transmission to the surface. A passing autonomous wave glider could interrogate the seafloor units. It would download the data without physically disturbing the instruments. This ingenious system completely bypassed the need for winter access. One observatory focused entirely on dissolved marine gas concentrations. An optical optode sensor measured oxygen levels near the vents. Another specialized chemical sensor tracked carbon dioxide output continuously. The Iceland Vents release significant amounts of natural greenhouse gases. Understanding this deep natural carbon cycle is scientifically crucial. Dr. Victor Gallardo oversaw the complex geochemical data analysis. He noticed distinct tidal influences on the daily venting rates. Low ocean tide correlated with significantly increased fluid discharge. The reduced water pressure allowed more trapped gas to escape. These continuous measurements revealed complex rhythmic patterns in the deep. The deep ocean clearly operates on its own hidden schedule. Advanced materials science played a huge role in these deployments. Standard steel corrodes rapidly in highly acidic hydrothermal vent fluids. Engineers utilized specialized ceramic coatings for the delicate temperature probes. Synthetic sapphire glass protected the expensive high-definition camera lenses. Aggressive biofouling presented another major engineering challenge for the team. Tube worms and bacteria quickly colonize any available hard surface. Mechanical robotic wipers periodically cleaned the sensitive optical glass sensors. Copper-infused marine paints deterred biological growth on the titanium frames. These crucial innovations ensured the delicate instrument survived the year. The Meteor returned in 2016 to safely recover the drives. All 3 seafloor observatories functioned perfectly throughout the dark winter. Recent scientific expeditions utilize even more advanced autonomous technology. The AUV Abyss conducted extensive mapping surveys in 2019. This sleek torpedo-shaped robot glided silently above the active vents. It mapped subtle magnetic anomalies in the fractured basaltic crust. Hydrothermal alteration permanently changes the magnetic signature of volcanic rocks. The AUV flew just 50 meters above the tallest chimneys. It maintained a constant altitude using forward-looking obstacle avoidance sonar. The resulting high-resolution magnetic maps revealed deeply buried fault lines. These hidden geological structures dictate where new vents might form. The ambitious expedition covered over 200 square kilometers total. It remains the most detailed geophysical survey of the area. Sampling techniques also saw dramatic technological improvements very recently. The ROV Keel 6000 introduced a revolutionary new suction sampler. This specialized device acts like a gentle underwater vacuum cleaner. It carefully collects fragile organisms without crushing their delicate bodies. Rotating acrylic carousels store the biological samples in isolated chambers. A precision laser scaler projects 2 green dots onto targets. These bright reference dots sit exactly 10 centimeters apart always. This allows biologists to measure deep-sea organisms accurately on screen. High-resolution 4K cameras capture every minute detail of the ecosystem. Scientists can easily identify tiny limpets living on the chimneys. The recorded visual data alone provides years of research material. International collaboration heavily defines modern Iceland hydrothermal vent research. The Global Interage program coordinates these incredibly expensive deep-sea missions. Dedicated scientists from Germany, Norway, and Iceland share valuable resources. Open data repositories make findings available to the global community. The unique crustal thickness near Iceland creates unusual venting chemistry. Geologists constantly compare these specific sites to the mid-Atlantic ridge. The massive mantle plume beneath Iceland alters the magma composition. Expeditions constantly test the hot fluid samples for trace metals. These microscopic elements offer vital clues about deep mantle dynamics. The technological evolution of deep-sea research is truly remarkable. We moved from blind mechanical dredging to precision robotic sampling. Every scientific expedition to the Iceland Vents yields new surprises. The extreme deep environment pushes engineering to its absolute limits. Scientists spend many months preparing for a single ROV dive. Equipment must withstand crushing hydrostatic pressure and highly corrosive fluids. Researchers slowly piece together the incredibly complex geothermal puzzle. The Kolbeinsey Ridge remains a vital and pristine natural laboratory. Scientific exploration here will definitely continue for many generations to come. The Reykjanes Ridge vents differ from global counterparts. The Pacific hydrothermal fields sit at immense depths. The East Pacific rise reaches 3,000 meters down. Icelandic vents often exist much closer to the surface. The Streiton field peaks at just 50 meters deep. Shallow depths alter the local boiling point significantly. Deep Pacific vents produce fluids exceeding 380 degrees Celsius. Icelandic geothermal emissions generally reach 250 degrees Celsius. The mineral composition varies across these global fault lines. Mid-Atlantic ridge vents expel heavy iron and manganese. Icelandic structures contain higher concentrations of silica and magnesium. High magnesium creates distinct white chimney formations underwater. Pacific black smokers build massive sulfide towers over millennia. Icelandic white smokers grow much faster in comparison. Some local chimneys add 10 centimeters of height annually. Scientists compare these ecosystems to the Mariana Trench. The Mariana Vents endure extreme hydrostatic pressure continuously. Iceland Vents experience relatively mild water column weight. The biological communities reflect these physical differences perfectly. Pacific Vents host giant red tube worms everywhere. Rifsha Pachyptila dominates those distant southern ecosystems entirely. Icelandic hydrothermal fields completely lack these tube worms. Local vent biology relies on different foundation species. Mats of chemosynthetic bacteria cover the basalt rocks here. Small gastropods graze continuously on these bacterial layers. Marine scientists map these distinct biogeographical provinces globally. The Atlantic circulation patterns isolate these northern species. Ocean currents prevent larvae transport from southern vents. This isolation creates a highly unique genetic reservoir. The Arctic Circle acts as a strict biological boundary. Protecting these delicate underwater structures requires international cooperation. The OSPAR Convention designates specific marine protected areas. Iceland recognized the vulnerability of these vents early. The Stryton Field received full legal protection in 2001. It became the first protected underwater monument globally. Before protection, commercial fishing caused substantial structural damage. Bottom trawling nets easily crush the fragile silica chimneys. A single net can destroy thousands of years of growth. Recreational divers also posed early risks to shallow vents. Careless fin kicks broke off delicate mineral spires. Conservation laws now strictly regulate human access here. Vessels cannot drop anchors within the protected boundaries. Scientific sampling requires specialized permits from the government. Researchers must justify every single piece of rock removed. Marine biologists monitor the recovery of damaged chimneys. Time-lapse cameras document the slow rebuilding process daily. Mineral precipitation gradually heals the broken chimney tops. Full recovery of a major spire takes several decades. National environmental agencies track local water quality continuously. Thermal pollution from nearby terrestrial plants remains a concern. Changes in ocean acidity threaten the calcifying organisms. Snails living near the vents possess fragile shells. Increased acidification could dissolve their protective outer layers. Conservationists advocate for expanded buffer zones around the vents. The Grimsey Island thermal fields need similar legal shields. Protecting the ocean seafloor preserves essential biodiversity hotspots. These vent fields function as deep ocean oases. They support marine life miles away from the thermal source. These hydrothermal fields offer vital clues about early Earth. Scientists study them to understand the origin of life. Alkaline vents produce conditions similar to the primordial ocean. A chemical process called serpentinization occurs constantly here. Seawater reacts with exposed mantle rocks beneath the crust. This reaction releases large amounts of hydrogen gas. Hydrogen provides essential energy for primitive metabolic pathways. Dr. Michael Russell first proposed the alkaline vent hypothesis. He suggested life began in these porous mineral structures. The mineral walls act as natural cell membranes. They concentrate organic molecules in tiny microscopic chambers. Thermal gradients drive chemical reactions within these rock pores. This environment perfectly supports the RNA world hypothesis. Researchers search for the last universal common ancestor. Biologists refer to this theoretical organism as LUCA. LUCA likely evolved in a hydrothermal vent environment. Genomic studies show LUCA depended on hydrogen and iron. Icelandic vents provide the exact chemical cocktail needed. Scientists collect fluid samples to study abiotic synthesis. They observe amino acids forming without living organisms present. Extreme heat and pressure force carbon and hydrogen to bond. These simple organic compounds form the building blocks of life. Astrobiologists apply this research to other planetary bodies. Jupiter's moon Europa likely harbors similar hydrothermal vents. Saturn's moon Enceladus shoots plumes of water into space. Cassini spacecraft data revealed silica nanoparticles in those plumes. These particles strongly indicate active hydrothermal vents on Enceladus. Studying Iceland vents helps prepare for deep space exploration. NASA engineers test underwater rovers in these extreme fields. The Orpheus submersible navigates the rugged volcanic terrain. It uses advanced visual odometry to map the seafloor. This technology will eventually explore Europa's subsurface ocean. The extreme temperature gradients test sensor durability perfectly. Astrobiologists study the extremophile bacteria living in the vents. These specialized microbes survive intense heat and toxic chemicals. They provide a biological template for potential extraterrestrial life. If life exists elsewhere, it might resemble these archaea. The methane-producing bacteria here require no sunlight whatsoever. They extract all necessary carbon directly from volcanic gases. This chemolitho-autotrophic lifestyle could sustain life on dark moons. Exploring these northern vents presents severe technical challenges. The ambient oceanic water temperature hovers near freezing. Fluids exiting the rocky vents exceed 200 degrees. This extreme temperature gradient stresses delicate mechanical equipment. Titanium housings protect sensitive electronics from massive thermal shock. The ROV Jason requires constant maintenance after vent dives. Corrosive sulfuric acid degrades external cables and connectors quickly. High mineral content clouds the expensive camera lenses immediately. Pilots must navigate blindly through thick black smoke. Strong localized currents push the heavy submersible off course. The Reykjanes Ridge features highly unpredictable underwater weather. Magnetic anomalies severely disrupt standard compass navigation systems. The iron-rich basalt rocks confuse the onboard directional sensors. Pilots rely entirely on acoustic positioning beacons instead. Deploying scientific equipment requires precise timing and coordination. The research vessel Atlantis maintains position using dynamic thrusters. Surface waves in the North Atlantic are notoriously violent. 10-meter swells often force expeditions to halt operations entirely. The fiber optic tether connects the ROV to the ship. This vital cable must maintain exact tension at all times. Too much slack causes tangles on the jagged rocks. Too much tension snaps the critical communication link instantly. Sampling the vent fluid requires specialized titanium syringes. Standard plastic or glass containers would melt instantly here. The isobaric gas-tight sampler captures fluids at ambient pressure. This prevents dissolved gases from escaping during the ascent. Maintaining exact pressure is crucial for accurate chemical analysis. Mapping the vent fields demands advanced sonar technology. Autonomous underwater vehicles glide smoothly above the chimneys. The AUV Sentry uses multi-beam echo sounders to create maps. It flies just 50 meters above the jagged terrain. The vehicle must avoid colliding with tall mineral spires. Programming the flight path requires extreme mathematical precision. Scientists process terabytes of raw acoustic data daily. High-resolution maps reveal previously undiscovered hydrothermal vent clusters. Acoustic imaging penetrates the thick hydrothermal plumes easily. Optical cameras fail completely when the water becomes too turbid. Laser scanning provides millimeter-scale models of the rocky chimneys. These digital twins allow researchers to study structures safely. Deep ocean technology evolves rapidly with every new expedition. Hydrothermal vents act as massive underwater chemical factories. They concentrate valuable heavy minerals on the ocean floor. Seafloor massive sulfide deposits accumulate over thousands of years. These dense deposits contain high grades of copper and zinc. Gold and silver also precipitate from the cooling fluids. Mining companies express strong interest in these mineral reserves. The economic value of these deposits is historically unprecedented. Extracting these resources poses severe environmental dilemmas globally. Mining operations would completely destroy the delicate vent ecosystems. Plumes of disturbed sediment would smother nearby filter-feeding organisms. The International Seabed Authority regulates mining in international waters. Iceland controls the resources within its exclusive economic zone. Policymakers balance economic potential against ecological preservation carefully. Biological resources often hold more value than extracted minerals. Bioprospecting explores the genetic potential of deep vent organisms. Extremophile bacteria produce unique and highly resilient enzymes. These biological enzymes remain stable at extremely high temperatures. The biotechnology industry uses them for vital industrial processes. Polymerase chain reaction testing relies on such heat-stable enzymes. The famous Taq polymerase originated from a similar hot spring. Icelandic vent microbes offer new possibilities for medical research. Scientists screen these bacteria for novel antibiotic chemical compounds. The harsh competition for resources drives chemical warfare underwater. Microbes produce unique biological toxins to eliminate their rivals. These microscopic toxins often translate into powerful human medicines. Genetic sequencing reveals thousands of previously unknown protein structures. Pharmaceutical companies invest heavily in deep-sea genetic research. A single useful enzyme can generate billions in revenue. Patents on marine genetic resources raise complex legal questions. Developing nations demand equal access to these genetic sequences. The United Nations negotiates treaties regarding marine biodiversity sharing. Researchers isolate a new strain of Pyrococcus from Iceland. This unique archaean thrives at 100 degrees Celsius. Its enzymes break down complex carbohydrates incredibly efficiently. Paper mills use similar enzymes to bleach wood pulp. This biological alternative reduces the need for toxic chemicals. Green chemistry relies heavily on discovering new extremophile proteins. The hydrothermal vents represent an untapped library of biological solutions. Preserving these deep habitats ensures future scientific discoveries remain possible. Comparing global vents highlights the absolute uniqueness of Iceland. The Kolbeinsey Ridge extends directly north of the island. Hydrothermal vents here sit at mere 90 meters deep. Volcanic gas bubbles reach the ocean's surface visibly. This visual phenomenon rarely occurs in the deep Pacific. The lower pressure allows water to boil safely underwater. Boiling creates distinct phase separation in the rising fluids. Vapor and brine separate into completely different fluid streams. The thermal output of these vents affects global ocean currents. Heated fluids rise from the Kolbeinsey Ridge seafloor every day. This localized warming influences the surrounding Arctic water masses significantly. Oceanographers measure the heat flux at 40 megawatts per kilometer. Such immense energy alters the density of the immediate water. Lighter warm water ascends toward the freezing ocean surface rapidly. This upward movement creates microcurrents within the deep Denmark Strait. These localized flows interact with the massive East Icelandic current. Scientists map these thermal plumes using acoustic Doppler current profilers. Dr. Helge Bjornsson models this heat distribution across the basin. His collected data reveals subtle shifts in deep water formation rates. The Atlantic meridional overturning circulation relies on this cold water. Vent heat introduces a marginal but measurable variable right here. Beyond temperature shifts, these vents play a crucial chemical role. Basaltic rocks interact with dissolved carbon dioxide continuously under pressure. This process facilitates natural carbon sequestration in the deep ocean. Mineralization traps the carbon within solid carbonate rock structures permanently. Calcite and magnesite precipitate along the fractured oceanic tectonic plates. Dr. Sigurdur Gislason studies these rapid mineralization rates quite extensively. His research shows carbon solidifying in less than 2 years. The high pressure at 400 meters accelerates this reaction. Hydrothermal fluid chemistry provides a catalyst for this rapid binding. Silicate weathering consumes carbon dioxide from the surrounding cold seawater. This chemical sink helps regulate regional ocean alkalinity levels naturally. Benthic microbial mats further contribute to this vital carbon cycle. Chemosynthetic bacteria fix inorganic carbon into organic cellular material constantly. They utilize hydrogen sulfide as their primary metabolic energy source. This biological carbon pump operates entirely without any solar energy. The efficiency of this ecosystem fascinates marine biogeochemists globally today. Dissolved iron from the vents also fertilizes surface phytoplankton populations. Upwelling currents carry these micronutrients toward the sunlit photic zone. Diatom blooms rely heavily on this steady supply of iron. These microscopic plants produce oxygen and absorb atmospheric carbon daily. The deep sea vents indirectly support diverse life far above them. Every chemical exchange links the abyss to the global atmosphere. Oceanic circulation distributes these vent nutrients across the entire hemisphere. Helium isotopes from the mantle track these deep water movements. Researchers measure helium-3 concentrations to trace the hydrothermal fluid pathways. This rare isotope confirms the direct connection to Earth's mantle. Geochemists sample the water column at precise 10-meter depth intervals. They use specialized Niskin bottles mounted on a titanium rosette. Each water sample reveals a complex mixture of dissolved minerals. The data helps build comprehensive models of global ocean chemistry. Icelandic vents represent a critical node in this planetary network. Carbon dioxide dissolves more readily in cold Arctic surface waters. The ocean acts as a massive sponge for atmospheric gases. Deep water formation transports this dissolved carbon into the abyss. Hydrothermal circulation processes this carbon through complex subterranean chemical reactions. The basaltic crust acts as a massive geological chemical filter. Permeable rock layers allow seawater to penetrate miles beneath the seafloor. Magma chambers heat this fluid to extreme boiling point temperatures. The superheated water dissolves minerals from the surrounding crustal rocks. Buoyancy forces this mineral-rich fluid back toward the ocean floor. It emerges through the vents as a dark, cloudy plume. Many questions about these northern hydrothermal fields still remain unanswered. Future research expeditions plan to target unexplored Arctic ridge sections. The research vessel Arne Freriksen will depart next summer season. Scientists intend to map the seafloor at 67 degrees north. They will deploy the autonomous underwater vehicle named Gavia there. This torpedo-shaped robot carries high-resolution multibeam sonar mapping arrays. It maps the complex bathymetry with incredible centimeter-level acoustic precision. Researchers hope to locate entirely new vent fields further north. Another planned mission involves the remotely operated vehicle named Eager. Engineers upgraded its titanium robotic arms for delicate chimney sampling. The team wants to collect intact structures from Grimsey Graben. Isotope analysis of these structures will reveal their exact age. Geochemists suspect some chimneys have vented continuously for several millennia. Biological research will also utilize new environmental DNA sequencing technology. Scientists filter seawater to capture free-floating genetic material left behind. This method identifies species without requiring physical biological specimen collection. Dr. Eva Ramirez Lodra leads the benthic biodiversity acoustic assessment program. Her team sequences the genomes of rare thermophilic archaea strains. They look for unique enzymes capable of surviving extreme conditions. Industrial biotechnology companies monitor these genetic discoveries very closely indeed. Such enzymes might improve high-temperature manufacturing processes on dry land. However, the primary scientific goal remains pure fundamental ecological understanding. Biologists want to track larval dispersal between isolated vent fields. They deploy acoustic transponders to monitor deep ocean bottom currents. These sensors measure water movement at a depth of 1 kilometer. Understanding these pathways explains how tube worms colonize new vents. Researchers also plan to install permanent seafloor observatories right here. Cabled networks will transmit live data back to coastal laboratories. Sensors will monitor fluid temperature fluctuations in precise real time. Seismometers will record micro-earthquakes along the active mid-Atlantic ridge. These constant tremors indicate shifting magma chambers below the crust. Continuous observation will reveal how vents respond to tectonic events. Geologists hypothesize that earthquakes can suddenly alter vent fluid pathways. A blocked conduit might extinguish a thriving biological community overnight. Conversely, a new fissure could birth an entirely new ecosystem. Long-term monitoring provides the only way to witness these changes. The integration of artificial intelligence will process this vast data. Machine learning algorithms can identify subtle patterns in seismic activity. They predict volcanic unrest before thermal anomalies become visually apparent. This technological leap transforms deep-sea oceanography completely in modern times. Engineers develop new battery systems for extended autonomous underwater missions. Lithium polymer cells allow rovers to survey the seafloor for months. Sapphire glass domes protect high-definition cameras from the crushing pressure. LED arrays illuminate the absolute darkness with brilliant white light. These tools capture unprecedented footage of deep-sea animal behavioral patterns. Marine biologists analyze hours of video to understand feeding strategies. Every expedition expands our knowledge of this hidden alien world. Researchers want to understand the exact lifespan of these vents. Some fields might remain active for tens of thousands of years. Others might extinguish rapidly after a minor localized seismic event. Dating the mineral deposits provides a timeline of past activity. Uranium-thorium dating techniques measure the decay of radioactive isotopes accurately. This data helps reconstruct the geological history of the ridge. Oceanographers also study the unique acoustic signature of the vents. Boiling fluids create distinct high-frequency sounds in the deep water. Hydrophones record these acoustic emissions to monitor vent flow rates. Changes in sound frequency indicate variations in subsurface fluid pressure. The contrast between the surface and the abyss is profound. Above the waves, Arctic winds freeze the rugged Icelandic coastline. Below the surface, superheated water melts the surrounding basaltic rock. This duality creates one of the most extreme environments known. Life thrives here against all conventional biological and chemical expectations. These organisms rewrite our understanding of planetary habitability limits completely. Astrobiologists study these vents to model potential extraterrestrial life forms. Moons like Enceladus might harbor similar hydrothermal systems beneath ice. The Icelandic vents offer a reachable proxy for alien oceans. Europa could possess a similar silicate seafloor with active volcanism. Studying terrestrial extremophiles prepares scientists for future space exploration missions. Yet, these unique deep-sea ecosystems remain incredibly delicate and fragile. Human industrial activity now extends its reach into the deep ocean. Deep-sea mining proposals threaten many global hydrothermal vent sites today. Companies seek the massive sulfide deposits rich in valuable copper. Extracting these minerals would destroy the delicate chimney structures completely. The resulting sediment plumes would smother surrounding filter-feeding marine organisms. Noise pollution from mining machinery would disrupt marine mammal communication. Conservationists work tirelessly to protect the Kolbeinsey Ridge benthic habitats. The OSPA Commission recently designated several new marine protected areas. These legal frameworks restrict destructive bottom trawling and mineral extraction. Dr. Lisa Levin advocates for strict international deep ocean conservation regulations. She emphasizes the irreplaceable nature of these ancient biological communities. Once destroyed, a hydrothermal ecosystem might never fully recover naturally. The slow growth rates of deep-sea sponges make them vulnerable. Protecting these sites preserves a vital part of Earth's heritage. Their intrinsic value far outweighs any short-term economic resource extraction. We must respect the silent equilibrium of this submerged world. The deep ocean regulates the entire planetary biosphere quite quietly. Every undisturbed vent contributes to the stability of the whole. Recognizing this interconnectedness fosters a deeper global environmental stewardship ethic. The International Seabed Authority faces crucial decisions regarding these habitats. Scientists urge policymakers to establish comprehensive no-mining sanctuary zones immediately. Baseline environmental studies must precede any commercial exploitation of resources. The precautionary principle guides modern marine conservation strategies very effectively. Preserving the genetic diversity of the abyss benefits future generations. These unseen landscapes hold immense scientific and intrinsic ecological worth. Marine protected areas require strict enforcement to remain truly effective. Satellite tracking systems monitor fishing vessel movements near these coordinates. International treaties provide a legal framework for prosecuting illegal activities. Public awareness campaigns highlight the hidden beauty of these ecosystems. Documentaries bring the remote abyss into living rooms worldwide today. Education fosters a sense of connection to the deep sea. People naturally want to protect the environments they truly understand. The Icelandic government recognizes the scientific value of these habitats. They fund continuous research to map and monitor the vents. National pride in these unique geological features drives conservation efforts. Our journey through the Icelandic hydrothermal fields concludes right here.